All right, so this is kind of a continuation of yesterday's lecture, right? We started talking about, or we figured out some equations for what the charge on a capacitor is as we charge it through a resistor in an RC circuit, and we figured out an equation for the derivative of that, which is the current that's flowing through the circuit as we charge a resistor, and we found that they were both exponentials, and we found that by solving the differential equation that we got from applying Kirchhoff's rule to the loop of the circuit. And we're going to do a very similar thing today, but this time we're discharging the capacitor. So what we have is a circuit like this. No battery, right? So we've got a capacitor and a resistor here. The capacitor we're assuming starts out charged, so there's some charge Q. We'll call it Q initial, so that's the charge on the capacitor at time 0. There's a resistor in here, and then the question is, what's going to happen when we close that switch? What's going to happen to the charge on the capacitor over time? And what's going to happen to the current flowing through this loop over time? All right, well, before we apply any equations, can we maybe kind of qualitatively guess or describe what we expect to happen here?
It's probably going to be the same as the battery.
Well,
in similar ways.
What battery?
As the one we did yesterday, I think.
Okay, there's going to be some similarities between this and what we have yesterday, but in this case, well, yesterday we started out with a capacitor that had 0 charge on it, right? And when we connected the circuit with the battery, charge slowly built up on the capacitor until its potential asymptotically approached the potential of the battery.
I'm assuming it's going to be the reverse.
The reverse, okay, that's not a bad idea. So instead of charge slowly building up on the capacitor, what would be happening?
Maybe it's going to be quickly discharging first, and then at the end it's just going to slowly discharge because there is enough potential difference to like push them.
Okay, so you think that it's going to discharge quickly at first, so the charge will kind of decrease relatively fast at the beginning and then kind of slow down as we get near to the end. So that sounds pretty reasonable, because at the end there is less potential difference across the capacitor, so we might expect the current to get smaller and smaller, right? And then after a really long time, we would expect there to be no more charge on the capacitor, right? Because remember, we've got plus Q on one of these and minus Q on the other one. So as soon as we close this circuit, right, the positive charges are, well, really the negative electrons are going to move around the other way, but it's equivalent to the positive charges flowing through the circuit and making their way towards the negative charges, where they'll cancel those out. All right, so we are going to expect the charge to start at its initial value and decrease quickly at first and then slowly later on, right? And we might expect it to be a similar exponential function to what we saw yesterday. So why don't we find out? And we're going to do this exactly the same way as we did yesterday. We started by writing down Kirchhoff's loop rule, and then turning that into a differential equation and solving it. We're going to do the same thing here right now. The only difference is when we apply the loop rule, now there's no battery, there's no EMF. But we still want to go around the circuit and add up all the potential differences, right? Remember, the loop rule, all that says is the sum over any loop. The sum of the potential differences equals 0. So let's go around the circuit here. And let's assume this is my plus Q plate and this is my minus Q plate. So as I go from the plus Q side of the plate to the minus Q side of the plate, what's the change in potential difference across the capacitor? If I know I have a capacitance C and the charge on it is Q, charge on either plate. use your equation sheet. We should be able to do this. We know this just comes from the definition of capacitance. Remember, capacitance is defined as how much charge the capacitor can store per volt of potential difference across it.
Yeah, so it would be the charge divided by capacitance.
Yeah, so the potential is just going to be the charge divided by the capacitance.
Oh, I thought I said that.
Oh, sorry, maybe you did, and maybe it just didn't. I didn't hear it. Yeah, charge divided by capacitance. And is it going to be positive or negative? I'm gonna say I'm going around the loop this way. So from here to here, I'm going from a higher potential to a lower potential. These lights. Higher potential to a lower potential. Is that going to give me a positive Q over C or a negative Q over C? You're decreasing, right? Higher to lower means I'm decreasing the potential. So the first term is minus Q over C. And again, I'm going to indicate that this is a function of time, right? Charge is a function of time here. So I'm just putting Q of T to remind us of that fact. Of course, capacitance is the capacitance of the capacitor. That's a constant, right? That's not a function of time. And I come around the circuit and I find my resistor here. And what's going to be the potential difference as I go from this point here to this point here?
It's going to be the same as the potential difference we got before.
Well, yeah, but that's what we're going to get from the loop, right? The fact that when we add them up is equal to 0. But through any resistor, a resistor R, what's the potential difference across that resistor in any circuit?
It's going to be the current times the resistance.
Yeah, current times the resistance, right? That's from just the equation mistakenly known as Ohm's law, right? Delta V equals IR. Right, so as we go from here, and again, we're going from a higher potential here. Are we going from a higher potential to a lower potential here? We should be going from, it's in the same direction, right? So we should be going from a higher potential to a lower potential. So again, we're decreasing our potential, and we go the current as a function of time, right? Current's going to be changing, so I'm going to put it as a function of time just to remind us of that, times the resistance R.
Technically, wouldn't it be increasing? Because we are, never mind, I'm not sure.
Well, we're going to see that if we assume that our current is flowing, well, we're going to assume our current flows. Okay, well, that's a good question. Yeah, we want to make sure. So if this is our positive plate and this is our negative plate, right? We're going to assume the current flows, and I should have made this more explicit, is going to be flowing around here, right? From positive to negative. Right, so in this case, am I saying that right? This is the direction of I that I'm assuming, because I'm going to assume that the current's going to flow from this positive plate to this negative plate. So, and then since we chose to go around, I guess I chose to go around the loop the other way, which is why this one was negative. We went from a higher potential.
So it'd just be positive.
Q. Well, yeah, it would be positive if I'm going, if I was going this way, right, in the direction of the current. But since I'm going against the current, it's negative. It's going to be negative, right? You're right. It's true that I'm going from a lower potential here to a higher potential, but I'm also going against the current. So from the lower potential to a higher potential would increase the potential difference, but I'm going against the current, so I have to make it negative. Maybe I didn't do that the clearest way, but it doesn't matter which way you pick the current. We're either going to get, and it doesn't matter, we'll either get positive Q over C plus IR equals 0, or negative Q over C minus IR equals 0. And I happen to do it this way, and we get negative Q over C minus IR equals 0. Okay. Questions about that, about the loop rule that we get here? Okay, so what I'm going to do now is remember that the current is remember that current I is just the derivative of the charge. Right, so I'm gonna do this. I'm gonna say, let's add this to both sides, so that on this side I have minus the current. I'm gonna call that just dq dt times R is going to equal the charge Q over C. And just to make it a little bit easier to read, I got rid of the explicit time dependence here. But Q is still a function of time, and dq dt, that's the current, that's the derivative, right? So this is what our loop rules gives us if we write it as a differential equation. So remember, what we're doing when we solve for a differential equation is I want to find what function, there's some function out there, Q of t, that if I divide it by C, I get the negative of the derivative of that function times R. Right, and there should only be, well, in some cases, there's more than one function that'll satisfy that. And we're also going to have to, put our initial conditions in here, that the initial charge is Q of 0 is this initial charge. All right, so when we're solving a differential equation, again, we're looking for what function of time, Q as a function of time, gives us, if we divide it by C, its own derivative times a minus sign times R. And the way we can find these simple, well, this is a simple one, believe it or not, we want to separate the variables and get kind of the Q's together and the terms without Q together, and then try to integrate both sides. All right. So let's try to do that. I want the Q's all together. So I'm going to divide both sides by Q. So I get minus, and then I'm also going to multiply both sides by dt. And I'm also going to, well, let's do that. Let's do it in a couple of steps. I'm going to divide both sides by Q. So I get minus dq over Q R equals, and I'm multiplying both sides by T. Whoops, got rid of the Q. So that's 1 over C dt. And then I'm going to move this minus sign and this R to the other side as well. So I'm going to have dq over Q equals minus 1 over RC dt. All right, so I'm just rearranging this to get the terms with Q over on one side and the terms without Q on the other side. And so far, this term should look familiar here, right? The RC in the denominator here. Do we remember what this is from yesterday?
Sir, could you repeat that, Mr.?
Yeah, I was asking, this RC should look familiar. Do we recognize this, the R times C from yesterday? What was this? RC.
The time constant.
That was the time constant, right? So it kind of makes sense. It's got units of time. So it makes sense that this goes along with the dt side here. And it looks like we're going to have a similar time constant in our solution today. So let's integrate both sides now, right? If we can integrate this side from 0 to Q to the Q of, and I'll put this as, yeah, it's not great to use the same variable in the limit as we're using over here. So we'll call this, Q of t, just to distinguish it. And this one we can integrate. Right, this is a constant, so I can integrate over here, 0 to t. And now I can do these integrals. The one on the left is just, you know what the integral of dx over x is, right? And what is that? What would the integral of dx over x or dq over q be? And actually, hold on, I'm going to be careful here. I'm not starting at 0, right? At 0, my q is my initial charge. And then at some time later t, I'll be at this charge. I want to make sure I have the right limits. But if we do the integral of 1 over x, or the integral of 1 over q, whatever variable of integration we're using, what do we get? What function has its derivative as 1 over the variable?
Natural log.
Natural log, right? Exactly, the natural log. So what I get here is the natural log of q. Evaluated at the initial and at q of t. And on this side, I get minus 1 over RC, and this is an easy integral to do, right? If I just integrate dt from 0 to t, what do I get there? Or what function? This is just 1 times dt, right? So what function has a derivative of just 1? If it was a function of x, what function of x has a derivative of 1? Sometimes people can do the derivatives if x is the variable, but not if t or something else is.
Isn't it just x?
It's just x, right? Or it's just t in this case, right? So if I integrate from 0 to t, I just have t, evaluated at t and at 0, right? So on this side, that's just going to be, t minus 0 is just t, so I get minus t over RC here. And here I get the natural log of q of t minus the natural log of q initial. And there's a property of natural logs where you subtract 2 natural logs. It's the natural log of those 2 things divided by each other. So this, what I get here is the natural log of q over t over my initial time is equal to minus t over RC. All right, let's move this down a bit. Are we okay with that? And that's because the natural log of, I guess I should have written it out, of q of t minus the natural log of initial charge is going to be equal to this, right? This is just a property of natural logs. I didn't go into detail in that yesterday because we had to do a u substitution to calculate that integral. This one's kind of simpler, so I wanted to do it out. Are there questions about the integral? I know not everybody is 100% familiar with doing definite integrals, but if you are, this should look familiar and make sense. And what would be the next thing I want to do? Remember, my goal here is to get q of t by itself, right? I want to find q of t. And I'm almost there now that I've done the integral. What's the next step?
You multiply by e, both sides.
Multiply by e, that's not quite correct. Because then I would have e times the natural log equals e times. I raise e to the power of both sides, right?
Oh yeah.
Exponentiate both sides. And if I raise e to the natural log of something, I just get that thing. So I get q over initial charge is going to be equal to e to the minus t over RC. Right. So then now I've got my answer for charge, right? I've multiplied both sides by my initial charge. So the charge as a function of time is just my initial charge times e to the minus t over RC. So there's that time constant again, right? The RC. So let's graph that real quick before we look at current. So here's charge as a function of time. I know that initially my charge is at this value QI. And then it decays exponentially, right? So this is just you know, when time is 0, e to the 0 or anything to the 0 power is 1. So that's right that I start out with just QI. And then as this gets bigger, as this goes to infinity, right, the exponential goes down to 0. So I do exponentially lose charge, and it's just as we predicted at the beginning. It starts out, we lose charge pretty quickly, and then as time goes on, this flattens out, right, and it asymptotically approaches 0. Sorry if I'm not making that clear on the screen. All right, so this is the discharge of a capacitor. Right, when we charge the capacitor, I'm just going to put up yesterday's for comparison. This was charging the capacitor yesterday, right? We started out at 0 charge, increased the charge quickly, and that kind of flattened off over time. And it asymptotically approached, you know, capacitance times the potential of the battery. And then as we discharge it, whatever charge we start at falls away exponentially. And the time it takes for that to happen has to do with our time constant again. Right? When time is equal to RC, we have e to the minus 1. E to the minus 1 is just a number that's approximately a third. So that means after RC amount of time has gone by, the charge is approximately a third of what it was when it started. After another RC amount of time goes by, the charge is a third of what it was then, and so on. Right? And you never quite get to 0 doing that, but you get pretty close. So the other thing we wanted to look at was the current as a function of time, and to do that, we just need to take the derivative, right? So we know that the current is dq dt. What do we get if we take the derivative of this? Does anybody know that? I hope so. The derivative of e to the x is just e to the x, right? So what's the derivative of a constant? E to the constant times x. We know that. If not, here's our equation sheet. Right? And we've got derivative of e times some constant to the x power is just that constant times e to the constant to the x power. Right? So in this case, our constant, our a, is minus 1 over RC. So that means the derivative, and we still have this QI in here as a constant, is going to be minus 1 over RC times the exponential that we had before. Questions about that? Does that make sense? Again, I don't know how far or how advanced. I assume it's in Calc AD that you do derivatives as exponentials, but that might not be true. So let me know if that's right. And then again, if we graph the current, how does the current change as a function of time? Well, it starts out, right, at time 0, when we first close it, e to the minus 0 or e to the 0, anything to the 0 is just 1. So our current, well, first of all, we got a negative value for the current, right, which means which means it's flowing the other way. Anyway, so here's the value of the current. Q at the magnitude anyway is QI over RC. And we know it's going to exponentially decay away to 0. So it's going to look a little bit similar, or a lot similar to the charge function, right? We start out with a lot of current, and it goes away, and eventually we end up with 0 current, right? Once the capacitor has discharged. And again, we have our last thing I'll say about this is we have the time constant again, which we call tau. Is the time constant. And that's the time for the current or the charge to fall to 1 over E of the initial value. Right, so a larger resistor in that circuit means it's going to take more time to discharge. That makes sense. A bigger capacitor, a bigger capacitance means it's going to take more time to discharge as well. Questions about the discharging of a capacitor?